Hi, my name is Aditya, and I'm excited to present to you our project, Valence-driven memory prioritization in machines. This project is in collaboration with Sofiya and Professor Josselyn, and supervised by Professor Laschowski at the Machine Intelligence Lab. Autonomous vehicles and robots suffer from a lack of long-term memory prioritization. Long-term memory prioritization can improve long-term thinking and planning for long-horizon tasks. Improving what these systems retain and what they don't is still an open challenge. There are two existing approaches. The first adds external memory buffers to serve as long-term memory. The second uses brain-inspired mechanisms. For example, this paper by Kim et al. From NeurIPS implements NMDA receptor-based activation functions for the feed-forward neural network of the transformer to change how the model retains memories. While both of these are valid approaches, unlike humans, neither approach leverages the emotional valence of a stimulus to decide if it is worth remembering. Our framework to address this consists of three components, inspired by the human brain. The first is neuromodulation, similar to dopamine or other neurotransmitters, that charge experiences with an associated emotion. This is implemented via a weighted cross-entropy loss, where the absolute value of the valence, which is a scalar value from -1 to 1, modulates the strength of the loss. Beta here is a hyperparameter that controls the strength of the modulation. Second is the amygdala, which changes how the scalar valence is represented within the model. Valences are projected into a rich embedding space, where similar valences produce more similar vector embeddings. Finally, we have the hippocampus, which modulates the retrieval of memories. This hippocampus module uses the embedding generated from the amygdala in its calculation. With this, the emotional signal of both the query and the key play a role in the long-term memory retrieval. We aim to recreate the graph in the bottom right. That being, we want the memory strength to be a function of valence, with more salient events being remembered better. In order to test the generalizability of our framework, we evaluated across three distinct tasks, that being a spatial memory task, an episodic memory task, and a language retrieval task. First is the spatial memory task. An agent takes a random walk through a 2x2 grid wall and learns to auto-regressively predict which observation it will encounter next. This is represented to the model as a sequence of action observation pairs, which is fed into an RNN transformer Excel, which we use as our baseline. We then test our framework incorporating the three novel mechanisms, the valence embedder, the valence-enhanced self-attention, and the weighted cross-entropy loss. We then evaluated the long-term memory accuracy of the predictions in this model. The second task we created is an episodic memory task, for which we created a synthetic dataset. Think of it as a room and the objects it contains. For example, if you walk into a room and you see a red chair, a blue fan, and a green table. Here, there's no spatial component. The model must associate a context with a sequence of observations. We train an encoder-decoder model where the encoder captures the full memory trace, and the decoder is given a causal prefix, and its goal is to autoregressively predict the next observation. Again, we incorporate all three of our novel mechanisms, that being the valence embedder, valence-enhanced cross-attention, and weighted cross-entropy loss. The third task is a language retrieval task. We trained a decoder-only model on Wikipedia articles, where the goal was to correctly recall a proper noun that had been observed prior in the text. In this example, the word dimus appears in this Wikipedia article, and 64 words later, the proper noun appears again. Valence was assigned with part of speech tags, where magnitude reflected semantic weight, and the sign recalled distinction, like singular versus plural. Only the first and second occurrence of a proper noun received the maximum valence value of 1 and -1. Everything else received valence values between -0.8 and 0.8. This, again, has all three of our novel mechanisms, including the valence embedder, the valence-enhanced self-attention, and the weighted cross-entropy loss. Here are results showing the long-term memory recall accuracy as a function of valence, similar to the brain diagram we saw before. This is shown for the spatial memory task, but the same pattern holds true for other tasks. The three columns represent increasing strengths of valence modulation, controlled by beta. The baseline is shown in gray. It's flat across all valence levels, as you'd expect from a model that treats all the information equally and without considering emotional valence. Every model that incorporates weighted cross-entropy loss shows an emerging V-shape, like we saw in the brain. Most importantly, it's our full model, the valet, shown in dark red, that outperforms the baseline at the extreme valence levels of -1 and 1. This is exactly the human-like memory profile we set out to produce. To understand how the valet achieves this, we analyze the attention scores grouped by valence level. The valet model, like the baseline, reflects a strong diagonal representing the observation identity. However, it shows two new features. One, the elevated attention scores in the corners, indicating that the model attends based on matching salience between keys and queries, meaning the absolute value of the valence. And two, a gradient through the heat map, indicating that the model is sensitive to similarity between neighboring valences. We then looked at the sparsity of the self-attention weights and found that the valet produces sparser attention overall. This likely means a higher signal-to-noise ratio, which could directly explain the improved recall performance. Finally, on the language retrieval task, on the left, you can see the example generations from both models. On the right, we plot the recall accuracy as a function of where in the text the proper noun first appeared. Across most steps, valid outperforms the baseline. And more importantly, we think that by assigning peak valence to sentences in the middle of long sequences, it should be possible to flatten this curve, achieving more uniform recall performance regardless of the position in the text. To summarize, our brain-inspired framework for memory prioritization is generalizable across tasks and models. All three mechanisms in our framework are necessary to improve high importance recall above the baseline, and this is achieved through attention score modulation by both valence and salience. Memory recall now follows a V-shaped relationship with valence as observed in the brain, and this enables the long-term prioritization of specific memories in machines. Thank you.